Hello everyone, welcome to the last chapter, Advanced Covariance. It's the last chapter with formal lecture, but I think it's also the most important one. You will learn some advanced model which can really do the multivariate analysis, which means we can analyze when the outcome variables are more than one at the same time. In this kind of situation, the variable we want to estimate, or the y we want to estimate, will not be a single value. It can be a pair or even a series of values. To tackle a problem like this, the concepts and codes are much more complicated than any other chapter in this textbook. Honestly, I didn't understand most of the content of this chapter when I was taking the multivariate analysis class last year. So I hope my learning experience can help you understand the material better. Also, I really recommend you to read the textbook, and it will help you understand the material of this chapter a lot better. In chapter 12, we learn about the construction of a varying intercepts model or multi-level model. In these models, there is only one parameter in each group. For example, in the chimpanzee example, we have three different groups of effect: the block effect, the chimpanzee effect, and the treatment effect. However, within each group, there is only one kind of variable. Like we only estimate the different intercepts between different chimpanzees and different intercept between different blocks. In this chapter, we will go one step further. We will learn about how to deal with the situation when we have more than one kinds of parameters in each group, and how to pull information between two kinds of parameters. I will use 4 different examples to illustrate these 3 different ideas. We will start from the simplest case when we have 2 intercepts in each group, and then we go more and more complicated. Let's begin from case 1. I know it's very hard to imagine in what kind of situation we will have more than one parameter under one group. Let's say we want to analyze the waiting time of 2 different cafes. You elite students must know that a cafe have peak time in the morning and non-peak time after. So we record the waiting time morning and afternoon as well. In this situation, we have 2 groups. That's the 2 different cafes, and we also have 2 intercepts in these 2 groups, meaning the waiting time in the morning and the waiting time in the afternoon. In the traditional approach we've learned, we will probably assign different priors for the 2 parameters, assuming they are independent from others. I mean, we have 1 prior for waiting time in the morning and 1 prior for waiting time in the afternoon. So we may have like 4 prior distributions for 2 groups and times 2 intercepts in each group. But the fact is that 2 parameters we are interested in, which means the 2 parameters of a certain cafe, they are probably related. We can imagine that at a more popular cafe, wait times are on average longer in the morning, but the same cafe will be much less busy in the afternoon since they have more staffs and fewer customers. But at a not so popular cafe, maybe they are not busy in the morning and they are not busy in the afternoon, so the difference will be small. This kind of information is very intuitive as for human beings like us. When we observe a popular cafe in the morning, it's very normal for us to guess the difference between average waiting time in the morning and in the afternoon will be a lot. However, to make a model to learn this kind of information, we need some mathematical tricks. We have to model their joint population, which means modeling their covariance. We need a distribution that can have a multivariate outcome. 2 parameters can be drawn together at the same time from that distribution. The distribution which makes this possible is a multivariate Gaussian distribution. I know the concepts are still very complicated, so in the first example, we will generate some fake cafe data and we will do backtests to make you understand how the model works better. Firstly, let's set the parameters for our fake data. What we need are the average morning waiting time and the average difference between morning and afternoon waiting time, and we also want a standard deviation for morning waiting and the standard deviation for the difference. Also, since we assume that waiting in morning and the difference are related, so we also need to set the correlation coefficient. Our assumption is that longer waiting time in the morning means larger differences the afternoon. But notice that the difference is negative, so the correlation coefficient is also negative. As I mentioned, since we need to estimate the 2 parameters at the same time, so we would like to draw the 2 parameters from one, so the distribution needs to have a multivariate outcome, or you can think of it as a multiple outcome at the same time. The most common distribution when we have a single outcome is normal distribution, or we can call it Gaussian distribution. When we are having multivariate outcomes, the most common multivariate distribution is also multivariate Gaussian distribution. It's actually very similar to the normal distribution we're familiar with. So in normal distribution, we have one value of mu and one value of sigma. But in multivariate Gaussian distribution, the mu is a mu vector, no longer have sigma, but we have a covariance matrix. The mu vector and the covariance matrix are very simple actually. So the mu vector are just the average value of the first parameter and the second parameter. And the covariance matrix, well, on the diagonal axis, it's the variance, first parameter and the variance of the second parameter. And on these two diagonal elements are the variance of parameter 1 and parameter 2. Or we can think of it as kind of the correlation between the two. The mathematical form of the 2D multivariate Gaussian distribution. So the mu vector is consisted of alpha bar and beta bar, which should be the 3.5 here and -1 here. And the first element in the covariance matrix is just sigma a square, so it's 1 square here. And the second and the third elements are the same. It's sigma a times sigma b times rho, so it's 1 times 0.5 times -0.7. And the last element is just sigma b is 0.5 square, which is 0.25. Instead of putting these four elements in the covariance matrix manually, so there's some mathematical tricks that can help us build the covariance matrix easier. So the covariance matrix can be decomposed into a matrix multiplication kind of sandwich form, because these two matrices are the same, and this is maybe the cheese between the two toasts. There is a convenient function that can do the kind of sandwich multiplication for us. And here is the R code for the above two methods I mentioned. The first method is the manually inputting method, so you have to memorize the position of each element. And the second method is the recommended one, so you can just use the diagonal and matrix multiplication, then you will get the correct covariance matrix. Now we are ready to simulate some cafes from the hyperparameters we have set. Let's use the multivariate normal function to draw 20 cafes as our simulated data. The output from the multivariate normal function is a 20 by 2 matrix, and each row is a cafe, so we in total have 20 rows, means 20 cafes. And the first column is the waiting time in the morning, and the second column is the differences between morning waiting time and afternoon waiting time. And to make it more convenient for future computation, I make the matrix into a data frame. So the result for varied effects is like this. And let's visualize the result from the multivariate normal distribution. Firstly, let's just look at the distribution of alpha and compare it with the normal distribution, with 3.5 being the mean and 1 being the standard deviation. As you can see, the two lines are very similar. And then let's look at the distribution B. It's also similar to the normal distribution, mean being -1 and standard deviation being 0.5, just like the hyperparameters we've set here. But how are A and B correlated with each other? So let's plot them together on a scatter. As you can see, they are negatively correlated. When we draw high alpha values, we will get a low beta value, and vice versa. So the multivariate normal distribution, or the 2D Gaussian distribution, look like this. If we look at it from the x-axis, well, it's a normal distribution. If we look at this multivariate normal distribution from the aspect of A, it's a very simple normal distribution with mean being about 3.5 and the standard deviation being 1. And if we look at it from the aspect of beta, it's another normal distribution with mean being around -1 and the standard deviation being around 0.5. If alpha and beta is not correlated with each other, the points should be scattered around, and the circles we draw will be like concentric circles, or you can say 同心圆. And these ellipses on the plot are the confidence interval of the multivariate normal distribution. Above are the simulated parameters. The above 20 pairs of alpha and beta are the average parameters of each cafe. You also need to draw some observations for each cafe. Let's say we will visit each cafe by 10 times, and 5 in the morning and 5 in the afternoon. So the resulting D cafe, which are the simulated observations, will have 200 rows, with 100 rows in the morning and 100 rows in the afternoon. And each cafe will have 10 rows. So the final simulated data we will use to train our model will be like this, with 200 rows, and from cafe 1 to cafe 20 with 10 rows, 5 rows in the morning and 5 rows in the afternoon. And we only observe the waiting time in the morning and waiting time in the afternoon. I know you are probably very confused about what we've done, so before getting into the model, let's briefly review the processes been through. Mathematically speaking, what we did is that we simulated a series of waiting line for 20 cafe, and the waiting line is drawn from a normal distribution with mu. It varies between a different cafe, and for each cafe there will be a difference between morning waiting time and afternoon waiting time, controlled by beta. And the pair of alpha and beta for each cafe is drawn from a multivariate normal distribution. The multivariate normal distribution is constructed by 4 hyperparameters we set. First is the mu of alpha. Second is the mu of beta. So these two mean values are the average waiting time across all the different cafes. The parameters we set are the sigma for alpha and sigma beta, which shows the diversity between different cafes. And the last parameter is the correlation coefficient, which controls the relationship between alpha and beta for a certain cafe. If you understand all of this, you are only one step away from building the STEM model. That is, how to set the prior. It's not that hard because the prior for alpha, beta, sigma beta are just the same as we did in previous models. The only trick is about setting the prior for the correlation matrix rho. In this case, correlation coefficient is just one single number because we only have 2 parameters that are related with each other. However, for some more complicated cases, we may have like 3D correlation matrix. But you don't need to worry about that because we will learn about a new distribution called LKJ distribution. LKJ prior works with any kind of correlation matrix. As we usually do, let's draw some samples from the LKJ distribution. Plot the shape of this distribution first. We can use random LKJ correlation function to draw random samples in R. There are 3 parameters in the random LKJ correlation function. First, n means how many samples you want, and k means the dimension of your correlation matrix. So in our case, the correlation matrix is a 2x2 matrix, so k equals 2. And the third parameter, eta, is the most will control the shape of our LKJ correlation, like the standard deviation in normal distribution. After executing the code, let's see what the output looks like. So firstly, we can check the dimension of the output. As you can see, it's 1000 times 2 times 2. So it means there are 1000 2x2 matrix. Each matrix looks like this. And if we change k to 3, the dimension of the output will be 1000 times 3 by 3. And each matrix will look like this. On the diagonal axis, the value must be 1. These two values are the correlation between parameter 1 and 2. These and these are correlation between 1 and 3. This is 2 and 3. So this is how the LKJ prior generate the correlation coefficient for any correlation matrix in any dimension. Secondly, let's compare the effect of eta from eta being 1 to eta being 4. So we just use k equal to 2 to simplify our visualization. In a 2x2 correlation matrix, the only correlation coefficient is this value on the position of 1, 2. So we can use this method to extract all 1000 correlation coefficient from the LKJ prior. And then we can use density plot to visualize how eta value influence the shape of LKJ prior. When eta is 1, the prior is very flat, and when eta becomes larger from 1 to 4, the LKJ prior becomes narrower, meaning that we are more skeptical on the two tails of the distribution. Finally, we can start writing our STEM model now, but we still need some new coding techniques to deal with the matrix and the vectors in our model. So we will introduce a new data type called correlation matrix. It's core matrix in STEM. Although a correlation matrix is just an n by n matrix, but values in the correlation matrix data type are limited. For example, on the diagonal matrix, the values are all 1. Other values are also limited in the range of -1 to +1. Also, the correlation matrix must be symmetric. With this limitation, these limitations improve the performance of STEM in the sampling process. So it's better to use correlation matrix. The data part is the same, so our y will be the waiting time from each cafe, 200 rows of waiting time. Other two variables is the cafe and its afternoon or not. In the parameters block, we define the parameters for our likelihood function, or we can call it the first level parameters. So we have alpha and beta with length of a number of cafe and sigma cafe. These three variables form our likelihood function. Wait times is normally distributed with alpha plus beta times afternoon with the standard deviation of sigma cafe. And then we have to define our hyperparameters. The simple hyper alpha and hyper beta are the mean of alpha and beta across all the different cafes. And then we define the correlation matrix of dimension 2. Lastly, sigma par is the sigma value for hyper alpha and hyper beta. It's a vector of length 2. I define them together because there is a convenient way to convert the vector like this into a matrix like this, sigma alpha and sigma beta on the diagonal axis. These hyperparameters work together and build the prior for our alpha and beta in the first level parameters. In the transform parameters block, the code is a little bit complicated, but no worries, I will explain the code step by step to you. Form of the model, so you can easily compare the math formula and the stem code we use here. The goal of the transform parameters block is to transform the parameters we've defined to match the required data type of the multivariate normal function R, or instead. The y of the multivariate normal function must be vectors, so the y is the alpha cafe and beta cafe pair of one cafe, and the mu is also a vector of alpha mu and beta, and the covariance matrix must be a matrix. Let's define the variables required for the multivariate normal function first. Vector of y has rows the same as number of cafe. For each row of y, there are two elements, alpha cafe and beta cafe, so it's a vector of 2. Mu is a vector of 2 formed by alpha bar and beta. This matrix, a 2 by 2 matrix. Lastly, mu cafe is for this formula, we want to calculate the mu mean value for each cafe under different situations, like we do in the linear regression model, just calculating the mean value, our normal distribution. After the declarations, the y vector is still empty, so we need to fill up the y vector with the correct alpha and beta parameters we defined here. So alpha and beta are kind of two vectors. We need to make them pairs. So the first element in J row is alpha j, and the second element J row is beta j. The same logic also works on the mu vector. Mathematically, the covariance matrix is calculated by the kind of a sandwich multiplication of matrices. Instead, we have a shortcut called quadratic form diagonal matrix. So you just need to put the correlation matrix and the sigma values, and then this quadratic form diagonal matrix function will do the following calculation. Well, exactly the same as the mathematical formula here for us. In the last part, we just do the calculation for the linear function like we did here. In the model block, we can have everything together. So first line is the likelihood function for linear regression. This line, wait time follows normal distribution of mu cafe and sigma in cafe. And then the prior for alpha cafe and beta cafe follow multivariate normal distribution of mu and covariance. The y and mu and covariance metrics are defined in the transform parameters block. And then the sigma cafe, this value follows exponential 1. In the last part, we just define the prior distribution for those hyperparameters. After all the hard works, we can finally print our posterior and compare the results with the parameters we have set previously to see if the estimation is correct. It seems that the results are very close to our predefined hyperparameters. So alpha bar is like 3.76 compared with 3.5, hyper beta negative 1.1 compared with negative 1. This is how the multivariate normal function works. Results show that the model actually learned the negative correlation alpha and beta, even though it just only observed the wait time in the morning and after. So the backtest is successful. In the last part of case 1, I'm going to visualize the result from our complicated model and compare it with a simple model we are already familiar with. We can use very straightforward ideas for the simpler method. So here I just compute the mean of the wait time for each cafe in the morning and the afternoon separately, and subtract the morning wait time from afternoon wait time to get the mean difference. Code I use to generate such results. So I use the group by function to group by each cafe and the time of the day and summarize the wait time using mean. The first part of the result will be like this. So the first row is the waiting time cafe 1 in the afternoon, in the morning, and the second row is the waiting time for cafe 1 in the afternoon. Use the spread function to convert this long table to a wide table like this. So now we have one row for each cafe and one column afternoon waiting time and one column for morning waiting time. Difference column is the result from column 1 minus column 2. And then I plot the beta alpha on the left hand scatter plot and the morning time and afternoon waiting time on the right scatter plot. Actually, these two plots contain the same information but from a different aspect. We extract the samples from our complicated models to visualize the result, and we plot the result from stand output against the simple method. I believe you are already familiar with the codes here. We just use the select and apply function to extract the output from stand and plot the result on the same graph as the simple method, so we can have a result like this. So the blue points are the output from complicated model and the black points are the result from the simpler model. However, a plot like this didn't tell us the difference for each cafe. We can use the geometric segment function to connect the 2 points from the simple model and the complicated model. As you can see, we can tell that the differences between the simple model and the complicated model is huge. Besides, it seems that there is no pattern in the plot. The pattern is still unclear even if we plot morning waiting time against afternoon waiting time using the same logic. But after adding the ellipse representing multivariate normal distributions, the results are very clear. We can easily tell that the output from the multi-level model, the complicated one, shifts toward the center of the multivariate normal distribution, or the center of this ellipse. Does these two plots look familiar to you? It's the same shrinkage effect as we observed in last step where multi-level model can share information between groups, where multi-level model allows information to be shared between a group. In this case, information are shared between different cafes. The shrinkage logic is the same in the multivariate model. We can observe that black points that farther from the center of the ellipse experience stronger shrinkage effect because these points are like kind of outliers. Let's move on to the second case of this chapter. I know the first case sounds to be very complicated, but no worries, case 2 will be easier because it's just a small extension from the first case. In the first case, we only have one group and the parameters in the group are correlated with each other. And in the second case, now we have two groups of parameters and parameters inside these two groups are correlated. So we just need to have another multivariate normal prior distribution for the other group. Let me show you how similar the two models are. The likelihood function in the case 2 is a binomial model, and in the case 1 it's a normal model, but the only difference is that we need a logic transformation to transform the p to the real number line. So this line and this line is equivalent. And for the parameter, so the model of case 2, there are just 4 parameters in one group and there are 2 groups, but in case 1 there are 2 parameters in just one group. And then this is the covariance matrix for the first NVN distribution, and this is the second covariance for the second NVN, and the matrix multiplication is exactly the same as we did in case 1. With this in mind, I believe you can understand the model easier. In case 2, the data we use is again the chimpanzee data. In chapter 12, we use the chimpanzee data to learn the concept about multi-level model the first time. At that time, we have hyperpriors for actor, for block, for treatment effect separately. In this chapter, we can further investigate if there exists interactions among actor and treatment or block and treatment. In chapter 12, we have 7 chimpanzees with 4 treatments in 6 different blocks, but the chimpanzee effect under different treatments are the same. But in this chapter, any chimpanzee can have different reactions under different treatments. For alpha parameter, the chimpanzee effect will be a 7x4 matrix. 7 means the number of different chimpanzees, and 4 means there are 4 treatments. The interaction terms between block and treatment follows the same logic. So the beta parameters block effect will be a 6x4 matrix because we have 6 blocks and 4 treatments. We are not only having more parameters, but we also want to pull information among each pair of alpha treatment pair or block treatment pair. So we will use again the multivariate normal distribution as their prior distribution. Here's a quick review of the model we used chapter 12, and we can compare that with the model we used in chapter 13. The only different thing is that we now use the NVN distribution as our prior. Our assumption is that the output of one actor, or maybe in one block under different conditions, may be correlated. So our prior should be a 4-dimensional multivariate normal distribution, which means that it will generate 4 correlated outputs at once. And since we have 10 different chimpanzees, so we will draw 10 outputs from the same multivariate normal distribution. Now, let's turn to writing our STEM model. The data we use in the chimpanzee example are exactly the same as the one we used in chapter 12. However, there are some important differences in the STEM model. I make a quick comparison of the model we use in chapter 12 and the model we use here line by line. Let's begin by the parameters part. In both models, the parameters we need are the coefficients for the linear model, either here or here. From chapter 12 to chapter 13, the coefficients are extended from a 1D array, real alpha A, to a matrix like vector 4 with length A. Be careful that although the coefficients are in chapter 13 are actually metric, we can assign them the matrix data type, since the sampling function for the MVN distribution only accepts n-dimensional vector. In the transform parameters part, we calculate the P for each row of the data using the for loop and construct the covariance matrix sigma alpha and sigma beta using the quadratic form diagonal function. Calculating the P here is pretty much the same as calculating the P in chapter 12, but be careful, we now have two different indexes, one for actor and one for treatment. The last part is the model block. So likelihood function for chapter 13 and chapter 12 are the same, and for the first level prior, we now use multi-normal function instead of normal function. Notice that I just set the average effect for all the alpha values as 0, so I use a repeat vector function, so STEM will repeat 0 4 times. You can replace this repeat vector with other alpha bar vector you want. The purpose of this repeat vector is the same as the alpha bar here. For other hyperpriors like sigma alpha and sigma beta, they just follow the same distribution exponential 1. For the two correlation matrix, rho alpha and rho beta, we can just use the LKJ prior we learned in case 1. Here, I set a stronger prior with LKJ 4. Here, I set a stronger prior with eta being 4, which means I don't expect to see strong correlation between these parameters. So after all the hard work, we can finally fit our model with the data we have, and let's check the results. However, you will immediately notice that the model didn't fit very well. Even though I've set the iterations to 4,000 iterations, the R-hat value are still larger than 1 for some parameters, and the number of effective samples very small for some parameters too. All of this suggests that our model is not good. This is a result of the divergent transitions problem we had in chapter 12. If you exaggerate the divergent function, you will notice there are almost 1,000 divergent transitions. That's a huge amount of them. Again, the only thing that can help us solve the problem is to use a non-centered reparameterization. The bad news is that there isn't much explanation in the rethinking text, so the following are my personal understanding. So I cannot guarantee the correctness of the math details, but I will try to explain it in an intuitive way. In chapter 12, we decompose a normal distribution of alpha follows normal alpha bar and sigma alpha to something like alpha bar plus alpha times sigma alpha, while alpha follows a standard normal distribution. In chapter 13, we have to do something similar. We need to decompose a multivariate normal distribution. Follow the same logic in chapter 12. We also want to represent our output in the form of x equal to mean vector plus z times a. Think of A as something similar to a covariance matrix. There are some relationship between A and the covariance matrix, and z just follows a normal distribution. So we have to figure out the relationship between matrix A and the covariance matrix. The definition of a covariance matrix is very simple. It's the generalized version of variance. From your high school math, you know that variance x is defined as the average of the square of x minus mu x. There is another shortcut easier from memory. It's the average of the square value of x minus the square value of mean x. In Chinese, it's 平方的平均减掉平均的平方. Now we want our x in the form of mu plus z times a. Then how do we calculate the covariance of x? First, calculate the mean of z and covariance of z. It's very simple because z follows a standard normal distribution, so the expectation of z is just 0, and the covariance of z, or you can say the variance of z, it must be 1. Then how about covariance x? So from the definition on Wikipedia, the covariance x is defined as the expectation value of x minus mu times x minus mu x transpose. We can replace x using mu plus za, so mu just disappear in the formula. Now the covariance of x now becomes expectation value of za times za transpose. After rearranging the order of operation, we can find out that the expectation of z times z transpose is actually the variance of z, which equals 1. So covariance of X is equal to A times A transpose. Now the only problem we have is how to find out A matrix. A linear algebra technique called class K decomposition can decompose a matrix to the exact form we want. Of course, we can just decompose a covariance matrix into class K decomposition form. However, we still want to know the sigma and the correlation matrix. Interestingly, multiplying the sigma matrix with the class K factor of a correlation matrix will construct a class K factor of a covariance matrix. So now we have a correlation matrix. If we call the class K decomposition function in R, and we will get a matrix like this. You can try to multiply these two matrices and you will get the exact same correlation matrix here. And then we multiply the sigma matrix with the class K factor of the correlation matrix, and the result is like this. Magically, if you multiply this matrix with the transpose of itself, you will get the covariance matrix. The A we are looking for is just simply multiplying the sigma matrix with the class K factor of the correlation matrix. Here's the finalized version of the non-center model. We can compare the non-center version with the center version model line by line. The likelihood function is the same and the logic transformation is the same. We just use another form of multivariate normal distribution to replace the MVN notation in the centered model. The centered version follows the form of parameters follow multivariate normal mu sigma. And in non-centered version, parameters follows mu plus A times Z, and Z follows a standard normal distribution. And A is a result of multiplying sigma matrix and the class K factor of a correlation matrix. In centered version of model, the correlation matrix follows the LKJ prior. In the non-centered version model, we can use the same LKJ prior, but there is a special form called LKJ correlation class key instead. So the result from this prior is a class K factor, which means it's a lower triangular matrix. Or you can imagine that the result from LKJ prior will automatically be decomposed into this form of a class K factor. After my explanation on the math part, I believe understanding the stand code of the non-centered model will not be difficult for you. Just keep an eye on the dimension of the matrix and don't let the matrix multiplication fool you. In the parameters block, we define the hyperparameters and the parameters. In the centered version model, we define correlation matrix using the correlation matrix data type. And in non-centered version, since the correlation is from a class K decomposed LKJ prior, so the data type is class K factor correlation. This will force the result be a lower triangular matrix. Sigma alpha and sigma beta is the same. You may be a little bit confused about the parameters block, why I set the parameters to be Z alpha. That's because alpha, the parameters we actually want, is calculated by mu plus Z times A. We have to define Z first, and then in the transform parameters block, we can calculate A. Things get clearer if we look into the transform parameters block. So here we calculate the P and the alpha and beta. So alpha equals to mu plus Z times A. We use the diagonal pre-multiply function to calculate this. This function will make the first element it's a vector to a diagonal matrix and do a multiplication. Let's check the dimension of alpha. So Z alpha is a matrix of 8 by 4. Sigma alpha will be a 4 by 4 diagonal matrix. The class K factor of correlation matrix is also a 4 by 4 matrix. And okay, alpha is a 8 by 4 matrix. The dimensions of the matrix really matter because it will affect how we index in calculating P. So here, actor is at the first element and treatment is at the second element, because we have 4 treatments and we have A of actors. The rest of the model are just the same as the centered version, so I won't talk about it. After fitting the model, we can check how many divergent transitions we have. Luckily, we don't have any divergent transitions after the non-centered version of model. After solving the divergent transition problem, we can start to analyze our model. We would like to investigate the sigma actor and sigma block parameter. We can tell that the block effect has a smaller sigma value than the actor effect, and the shrinkage effect is different from pair of actor treatment combinations. For example, treatment 4 has the largest variance. In the last part, I want to visualize the model and compare these most complicated version of the chimpanzee model with the most basic one we had in chapter 10. Here you can see I copy and paste the model we used in chapter 10 and use the same code to generate the prediction. But for the model in this chapter, since we have different effects for different chimpanzee and different treatment, we have to use a group by function here, aggregate the result for each combination of actor and treatment. Since the effect of block and treatment is very small, so I just ignore them. After that, we can combine the results from model 10, model 13, and the observed data all together in one same plot. The black dots are the training data. The red dots and red lines are from model 10, and the blue dots and blue lines are from model 13, varying effect with interaction. You can notice that our posterior prediction does not just repeat training data we observe. There will be a shrinkage effect, which means our prediction will closer to p equal to 0.5 compared with training data. Chimpanzee 2 is the most obvious case. In any combination of treatment or block, the chimpanzee just pull left, so the observed proportion is just 1. But you can see that our posterior prediction just shrinkage inward. You may wonder what's the main value of the complex model, since our conclusion about the data is the same for simple model and complex model, that the treatment effect is not significant. The point is that this complex model will reveal the situation when a few individuals react to a certain treatment, which is especially useful in like a medical experiment. So this multi-level model can help us input more predictors and without the risk of overfitting, because information are shared between groups. The shrinkage effect is stronger, so our prediction will be more conservative even if we have more predictors. It's the end of the first part of tutorial chapter 13. Thank you very much if you really watch the whole video. There are too much information in this chapter and I really want you to understand, so that's why this tutorial video is so long. I really hope you like this video and learn better into chapter 13 with the help of this video.